Hello everyone, I'm Yoshihiro Yamazaki from Tohoku University. Today, I'd like to talk about filler prediction based on bidirectional LSTM for generation of natural response of spoken dialogue. Many researchers have tried to build human-like dialogue systems. Dialogue systems are the machines that can talk with humans. I think most of you have used a virtual assistant or a smart speaker. In particular, there has been a great deal of research into generating natural responses by using neural networks. To achieve human-like conversation, it is also important to express speech disfluencies, such as filler, in addition to the naturalness of generated responses. Fillers are short words used to fill pauses in speeches, such as or you know. March and others reported that dialogue systems that generate fillers give the user a more human-like impression. However, neural-based responses do not contain speech disfluencies enough, because the model is trained by using written language corpus. To achieve a neural-based dialogue system that generates fillers, one of the approaches is inserting the fillers into the sentences in the training data. A filler prediction model based on conditional random fields and an n-gram model has been proposed so far. This model inserts fillers into the input sentence. By inserting fillers into a written style corpus, we can expect to transform it into a spoken style. Now, I'd like to talk about an overview of the conventional filler prediction model. This figure shows an overview of the conventional filler prediction model. Here, the target language of this study is Japanese, but an English translation is provided on this slide for explanation. This model inserts fillers into an input sentence in two major processes. The first step is to predict the position where filler will be inserted based on the CLF. The next step is to predict what kind of filler will be inserted using an n-gram model. In the prediction of the insertion position by CLF, the label F means that a filler should be inserted immediately after a word, and the label O denotes the contrary. The features of the CLF are the current words, the preceding two words, the following two words, the POS tags, and the last two molars of the current words. In addition, positions of the fillers are sampled from the conditional probability distribution estimated by CLF. To predict the kinds of fillers for where label F is estimated, they calculate conditional probability P of filler Fi, given the preceding two words, Wi-2 and Wi-1. And just like when predicting the positions of fillers, kinds of the fillers are sampled from the conditional probability distribution estimated by n-gram model. This is an overview of the conventional model. Now, there are several problems with the conventional model I just described. That is, it only considers a part of an utterance. and predicts positions and kinds of fillers independently. The appropriate filler varies depending on the contents of the utterance. So, we use bidirectional LSTM to consider a whole utterance. Bidirectional LSTM is a type of a neural network often used to deal with a sentence in natural language processing. Then, the positions and the kinds of the fillers depend on each other. Thus, we model them concurrently. To sum up, we propose the filler prediction model based on BLSTM. In this study, we compare the performance between the proposed and the baseline model in terms of the prediction accuracy. This figure shows an overview of the proposed filler prediction model. The input is an utterance, and the output is the label of the corresponding filler. Here, the BOS token represents the beginning of the sentence. First, we convert each word in the input sentence into a word vector. The information in the sentence is then propagated forward and backward in BLSTM. The model outputs the filler forms at each time, if deciding to insert a filler after a given word, and the non-tokens otherwise. The network can model a relationship between the positions and kinds of fillers by considering them concurrently. In this example, the model outputs immediately after BOS, when the utterance "It's not my taste" is input. Therefore, the result of insertion is "It's not my taste." A spoken dialogue corpus is used for training and evaluation. During training, a filler removed utterance is used for model input, and the corresponding filler label is used for the output. The model is trained so that it can predict the original filler for the input utterances. Then, during inference, we obtained spoken style utterances by predicting filler labels for given utterances. Let's move on now to the objective evaluation experiment. We compare the performances of the baseline and the proposed model using precision, recall, and F-measure. We used the transcript of 345 sessions of multimodal one-on-one chat corpus for training and evaluating the model. This corpus contains spontaneous spoken dialogues between humans, and filler appears frequently. Here, we used 8 kinds of fillers, and these fillers are based on the result of morphological analysis. Then, we split the dataset into training, validation, and a test set by a ratio of 3:1:1. Since the fillers in each condition were thus imbalanced in number, so we balanced the number of the utterances by undersampling and oversampling. Consequently, we used 27,000 utterances for training set, 9,000 utterances each for validation set and test set. The training conditions for the models are as follows. The left table shows the conditions for the baseline model, and the right table shows the conditions for the proposed model. The input of the BLSTM was 300-dimensional water embedding obtained from the fast text model for Japanese. The network was trained to minimize the cross-entropy loss using Atom, and the parameters marked with star are determined by Optuna, that is the hyperparameter optimization framework. This is the result of the objective evaluation. These 8 lines represent the result of the evaluation for each filler. Mean denotes the mean scores of these fillers. Also, position is the evaluation results for the insertion position of the filler. Two major results can be seen from this table. One is that the proposed model obtained higher precision scores than the baseline model. The other is that recall scores of the proposed model are less than precision scores. I'd like to discuss the two major results. The first result suggests that considering the positions and kinds of the fillers concurrently is effective to improve accuracy. The second result indicates that the model hardly inserts fillers. One of the reasons is that the number of the non-tokens, which represent not inserting fillers, is greater than that of the filler tokens. So, we consider that increasing weights on the loss of filler tokens can prevent the model from generating too many non-tokens. To conclude my presentation, I'd like to sum up. We proposed a filler prediction model based on the BLSTM to insert the fillers into the written sentence. The results of the experiment suggested that the proposed model outperformed the baseline model. The future studies are described as follows. We will use a weighted cross-entropy loss to improve recall scores and conduct a subjective evaluation. In addition, we will implement other speech disfluencies prediction, such as a pause prediction. Then, we will use the sentences generated by the proposed model for training a neural conversational model. Thank you for your kind attention.